Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving an interesting equation with complex numbers. We have z times I to the power z equals 4, and we're going to be solving for z values. At this point you're probably guessing, hey, this is a solution that works, so on and so forth, but we're going to be looking at the general solution. Alright, and we're also going to be looking at some results from Wolfram Alpha at the end to check what it gives us. Now, when you have something like z times something to the z, it could be z times 2 to the z, z times e to the z, z times something to the z, and so on and so forth. You should be thinking about a very special function called Lambert's W function, right? Hopefully you're familiar with that. Let me go ahead and quickly introduce you to it. If you have something like z e to the z, and I shouldn't use a z here because we may not always get that. Let's just use t, e to the t, or maybe w, whatever. So Lambert's W function is basically the inverse function for t e to the t. So if you think about it like, okay, write this as Lambert's W inverse of t is equal to t e to the t, and call this function f, then Lambert's W function is going to be the inverse of f. Make sense? Provided that it's invertible, of course, because when you consider the graph of t e to the t, it's not always a bijection. So you kind of have to split it up into different intervals depending on the maximum minimum values, and then kind of have a piecewise defined function. But I'm just going to avoid those complexities and kind of give you an overall sense of what we can do to solve these kinds of problems. Now, whenever you have something like this, you're going to use Lambert's W, right? But we don't have t e to the t. At least we don't have a t or e. We have an I. But we can easily fix that. And for that one, you could definitely use the complex exponential. Now think about what I to the power z means. If z is a complex number, and obviously I is a complex number too, isn't it? So what is the definition whenever you have something like this? Well, you can write it as e to the power z ln I. Don't worry about the ln I at this moment, but anytime you have something like this, and obviously I could be replaced with any complex number w, in this case you would get e to the power z ln w. So that's the definition for our complex exponentiation, because how would you raise a complex number to a complex power, right? I mean, even raising something to an irrational power is kind of crazy. Complex will make it even crazier. So now we got e to the power z ln I, which is nice because at least we got closer to something like z to the z, because we have a z and then we have an e, so that's nice. Let's go ahead and do that conversion. Z I to the z equals 4. Awesome. Now we're going to replace I to the z with e to the z ln I, so it's going to be z times e to the z ln I equals 4. So far I only converted I to the z to something else, and now I'm going to go ahead and make our t, or should I say t e to the t, like tet. Now here's what we're going to do. Our t in this case happens to be z ln I, therefore we're going to go ahead and multiply both sides by ln I to get that. So z ln I times e to the power z ln I equals 4 ln I. Make sense? So we got our t, and now we can apply Lambert's W function on both sides, right? So let's go ahead and do that. I'm going to go ahead and put a W here, Lambert's W, and Lambert's W here. What is that going to give me? Let's find out. This is going to give me simply z ln I. And this is going to give me Lambert's W function of 4 ln I. Now, there's no way to calculate this directly because, you know, t e to the t doesn't have a simple inverse, but at least we can use a calculator, series approximations, so on and so forth, for finding a numerical value, right? In this case, Wolfram Alpha would be really helpful. I don't know if Desmos can do Lambert's W function. Maybe there's a way to do it. I haven't searched it out. Anyway, so we got this, and if we can go ahead and divide by ln I. But before we do it, let's go ahead and simplify this thing. Like, what is ln I, right? What is the log of a complex function? Well, the log of a complex function in general is defined as follows. If z can be written as, or I should probably use a w because z is already there. If w can be written as re to the I theta, theta being the argument and r being the modulus, then logarithm of w can be written as logarithm of the absolute value of w, which is ln r, plus I times theta. So that's basically the idea for this, and if you apply it to ln I, the modulus for I is 1, because if you think about the argand plane, the distance from I, or distance from 0, is 1 unit. This is the imaginary, and this is the real, as you can see. And of course, its argument is going to be pi over 2. But that's just the beginning, right? Not the end. So ln R, by the way, is going to be ln of 1, which is a real ln. That would be 0, and this would be pi over 2. So we don't have to worry about it. It's just going to be I times pi over 2. Nice. But I said it's just the beginning, right? What does that mean? It just means that pi over 2 is the principal argument, and you can always add multiples of 2 pi to it, where n is an integer. You're allowed to add and get infinitely many solutions. So this is multi-valued. There are infinitely many values for ln I. It's not a single value. Make sense? But you can just take the principal value for a particular solution. So let's go ahead and plug it in. We get z times ln I, which is I times pi over 2 plus 2 pi n. And then this equals Lambert's W of 4 ln I. Again, that will be 4 times I times pi over 2 plus 2 pi n. Again, that's the W of that. Let's go ahead and distribute and simplify a little bit. This is going to be the W of 2i pi plus 8i pi n. Okay, do you like that better? Now, on the left-hand side, though, we have z times something, I times pi over 2 plus 2 pi n. So what I need to do next is basically just divide by that, both sides, and you'll get the answer. So I can kind of do this. To get rid of the I, you could definitely multiply by negative I first, and then divide by this. Let's do it. So multiply by negative I, that's going to give you negative I times W of 2i pi plus 8i pi n, right? And then this is supposed to be a plus sign. And then all of that is going to be divided by pi over 2 plus 2 pi n. At this point, you can multiply the top and the bottom by 2 to get a nicer expression, but that's just no big deal. And as you can see, this is going to be an imaginary number, provided that this is going to be a nice real number. But is that going to be real? You'll see. Okay, anyways, let's go ahead and take a look at what Wolfram Alpha offers. And as you can see here, it gives us something similar, slightly different. And Wn is the analytic continuation of the Lambert's W function, so on and so forth. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time in another video. Until then, be safe, take care, and bye-bye.